So I'm recording now. Okay. Good morning, good evening, wherever you're joining from. You're able to see my screen, right? I see that.
Yes.
So I want to walk you through some of the terminologies very carefully. Yesterday I kind of gave you over, and I want to. Are you able to hear me well in terms of quality of call?
Yes, sir.
Okay, that's good.
Yes.
If you have difficulty, let me know. Okay, so yesterday I kind of walked you through what is factor analysis. Broadly speaking, I ran some examples and so on. And then today I want to nail the definitions. See, any science is all about knowing the terminologies. That's all, nothing else. Whether it's a law or mathematics. Okay, so and so is here too. And statistics, learning and machine learning, all they also have their own terminologies. So let us say that now we have 5 students. Okay, 5 students, and then they are doing 3 subjects, and these are the scores of their of those students. Okay, 5 students. So first, this is the story, the data, right? You should always ask for the story of the data, right?
Yes.
Student number 1 scores 3 points, 3 out of 10, let's say, okay, 3 points. And in finance, in marketing, he or she scores 6 points out of 10. In policy, the score is 5. So the 4th student is again 3. Okay, so these guys seem to have much correlation, right? 1 and 4.
Yes.
And in marketing, that student scores 9, and then in policy, the student scores 7. So like that, you interpret the data. So it's a very small data set. Just to know, you can do even hand calculation. That's the idea. Okay, and of course we can still use R. So I loaded this data already for simplicity, so that for ease. Okay, so this is called subject scores. Okay, sub scores. That means subject scores for me. So this is what it is. Do you see this one? Is this correct? 365, 733, 1098, 397,
397, 1065.
Now, I told you yesterday that what we are trying to do is we have scores, 3 scores for every student. Okay, 3 scores for every student, and we want to know what the underlying factors are. In this case, I'm only assuming only 2 factors. Okay, I cannot have too many factors because the maximum is it can be only 3 factors. Okay, because math, science, and marketing, right? Finance, marketing, and
Policy.
policy. Yeah. So it can be a good construction is either 1 factor or 2 factors. Okay. The lower the number, it is better. Okay, because you can explain easily. But then still, it needs to explain the variance, total variance, and total correlations. Are you with me? Okay.
Yes.
So, but we don't know what these factors are. We are assuming there is a factor, underlying factor, that explains these variations here, correlations here, and there is another factor, underlying factor. We don't know what it is, but those factors have some weights attached to it. So we neither know the factors, what it is, nor the weights. Okay, that's where it becomes kind of unidentifiable. Because it looks very strange, isn't it? We don't know this, 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 and then we are still saying this is what it is, right? It is very strange, isn't it? At least in regression, we know this is X variable, right? We know those.
Yes. Okay. Yes.
So this is what is going to create the non-uniqueness of the solution. Okay. So let's continue with this, and then we will figure out a way to fix the uniqueness. How to fix the uniqueness of the solution. So this is the structure that the scores of the students, remember that these are the scores of the students. So each of the scores of the students is has factors, 1 common factor and 2 common factors, F1 and F2. and their weighted values are beta 1, 1, beta 1, 2, beta 2, 1, beta 2, 2, beta 3, 1, beta 3, 2. With in neural network, this is called bias. We call this as intercept. Okay. All right. The whole idea is that, we have some idea, for example, that, this MBA program, finance is highly quantitative while marketing and policies have strong qualitative orientation. So we expect this kind of, some kind of a high loadings here together for, for the factor 2, for the marketing and policy scores, and factor 1 is going to be highly loaded with the value. Highly loaded means this beta 1 is going to be a high number, beta 2, 1, 2, 3, 1 will be going to be low numbers. Here it's beta 1, 2 is going to be low number, and beta 2, 2 and beta 3 is going to be high positive number. That's what loadings mean, expected loadings. Okay, some kind of understanding we have. Okay, so far so good.
Yes, sir.
Okay. How about you, Gaushali? Oh, yeah.
Yes, sir. Yeah.
All right. So, but what we are saying is that now this structure, we still have to, understand that these E1, E2, E3s are all errors because they are not going to be exactly same for every student, isn't it? So there are going to be errors here. There is a structure plus error, or that's always the model we use. Okay. So the errors are, with the expectation 0 and variance sigma I square. This is called specific error. Okay. This is called sigma I square is the error of the epsilon 1. Sigma 1 square is the error of the, variance of the error 1. Okay. Sigma 2 square is the variance of the error 2. Sigma 3 square is the variance of the error 3. And all of them have expectation 0 because this is what, centered. This is centered. So when you take it away, expectation will be 0. Now, we also have one more assumption, that is the unobservable factor fj's are independent of one another and of the error term. It is similar to regression, if you recall. This is also similar. This is also some regression type assumption. Okay, we don't have, these fj's or their x's are independent of one another and error terms. If it is not independent of one another, we get into multicollinearity. That's a separate problem. Okay. But this is the kind of information we also have it in regression. So this simplifies some of the computations in the formulas. That's the reason why we put that condition. Okay, it is not restrictive. Most of the problem it is approximately true. And remember, statistics is, and also even machine learning, is an approximate science. So it's not a restrictive assumption, restrictive understanding or condition. Okay. Now, so we wrote that YA. This model 3 equation is in simple form. I can write it like this. Agreed? YA is Y1 is beta 1 0 plus beta 1 1 F1 plus beta 1 2 F2 plus epsilon 1. That's what we wrote that. So like that. All these things can be in general written like this. Okay, and the variance of yi, each of the scores is, because it's a constant, it is 0. This is beta 1 square plus variance of f1 plus 1 2 square for 1, right? Y1 beta 1 1 square times 1 1 square variance of f1 plus beta 1 2 square variance of f2 plus variance of ei. These are all independent by the assumptions before. So it becomes like this. Agreed?
Yes.
Okay. Especially you too, right?
For me, the microphone, when I switch on, it takes some time to load it.
That's right. We see the variance of y consists of, there are two parts to this variance. So this is the loading related variance, right? Loading related. These are the loadings actually, not loading. So this is the factor related variance, okay, which are basically loadings. How much weight you have to give. That's what is called the loading. So this is factor related variance, and this is the error related variance. So we have a special name for that. That's called communality. Okay, this is the commonness. How much weight you have to give for yi, and for all the people, right? So that's where it is communality. And this is specific variance. Okay? Just a note there. Okay, naming. As I told you, this has also special words. So you can recall that communality means sum of squares of the coefficients or weights attached to the factors for each of the observation. Okay, in fact, this is the variable, you remember that, right? This is the variable, each of the, in this case, this is the score of, this is the score of marketing or policy or finance. So far, so good. Now,
Yes.
I can calculate, like what I calculated variance, I can also calculate covariances, right? So covariances, beta between I and J is, you can calculate that, so it's very straightforward. I will leave it to you because these are all the formulas you should have known, by learning statistics, right? Business opportunities and statistical analysis. You know how to calculate variance and covariances. This will become the cross product, right? Cross product between the y1 variable and yi variable and yj variable factor loadings. That's what the cross product is, right? B11, suppose you are looking at the finance and marketing, then finance is 1. Remember that, right? Finance is 1, marketing is 2. So B11 times this is B21 and this is B12 times B22. Are you with me? So that is
Yes, sir.
covariance. So I can fill up this whole thing here like this. All right. Now what we are trying to do is, there is a covariance, there is a variance covariance for this. There is a variance covariance for this, y1, y2, y3. And that variance covariance is split into two parts. Variance covariance attributable or explained by the factors, and variance covariance unexplained by these errors. This is similar to regression again, but we don't have an outcome variable. We have the blob of data. To recall your question, Nani, are you with me on that?
Yes.
The structure is you're right, but I would say, I don't want to say the regression structure, but you can say that because that's what it is in regression structure. But there we know what is F1 and F2 values are, but here we don't know. What I want to call it is that the y1, y2, y3 have linear relationship with hidden factors. The F1, F2 are hidden factors because we don't know them. Okay.
Okay.
All right. So we just say linear relationships. If that's what it means to you, regression, that's also fine. You can keep it. So that is a regression type relationship. So I can calculate for the given data set, I can calculate the variance covariance matrix. This is what it is. Everybody agrees?
Yes.
So, and so that is what I can calculate here. For this one, if I do that, covariance subscripts, right? All right.
Yes, sir.
So, when I calculate that, you see these values. They are just different from this. Okay? That is because this is sample values. This is the population. Okay.
Yes.
So there is some something is going on there. So I can get back to these numbers. You can see. So if I get back to this is multiply by 4 divided by 5. That's what population means. Okay. In other words, all the covariances and variances were n minus 1 in the denominator here. But here it is not n minus 1. That's why to get back to this one, I just need this one. Okay. Sorry. You know what the mistake is? You see, it is coming back to the same value. Agreed? So
Yes,
there is
sir.
some gadbada. They are doing it, but it should be sampled. That means I would rather work with this. But anyway, so the book is written like this. I will leave it. Okay. It should be sampled. That's why these symbols are S. Okay. Observed variance. Observed sample. That's the same as observed. Okay. So, but nonetheless, let's work with this. Whatever I'm going to explain it here, and then I will work with show some factor analysis codes here. Very simple codes. Okay. So what happens is that I have calculated the variance covariance. Okay. Are you with me, Nini?
Yes. Yes, sir.
Now, what I want to show you is that, there are lots of different factor loadings. Okay, lots of different factor loadings. In fact, infinite number of factor loadings I can create for the same data. So first, let me, calculate and show you how it is done, and then make sure that, I can explain how to standardize it. Are you with me? Standardize
Yes, sir.
it so that you don't have too many of them. You get one unique solution. Okay.
Okay.
All right. Yeah, this is not supposed to be like this. Okay, it is like this now. Correct. Okay. So here is one loading. Just as an example, I'm saying here is one loading. If I have like this, then I can calculate. You remember the variance covariance matrix? This is what it is, right? Variance covariance matrix.
Yes.
And I will get these things now by using, for example, beta 1 is this, beta 1 2 is this. So if you square this, sum this, you'll get 0.5. And then the variance of this one is sigma square. So here, if the factor loadings are like this, your variance cover matrix is like this. So that's what we here shows. For example, there is a y1. There is a y1 is 0.5 square plus 0.5 square plus sigma square. Okay, that's what this says. That's what this says. And like this, I can calculate for everything. The whole matrix I can calculate from this structure. That's what I'm saying. So from this structure, are you with me? I don't know. It's on fly. It's not. So is everybody with me? You and
Yes, sir.
okay, Nini, are you with this understanding?
I think so, but
What
I'm a
I'm saying
little,
is this.
yeah.
What I'm saying. Okay, go ahead.
I'm a little not clear
Okay.
right here.
So what I'm saying here is, if this is the structure, okay, if this is the loadings, just an example calculation I'm going to show. If this is the loadings, then I can get the variance covariance matrix from here because that's what this says, isn't it? I'm just using all this formula here for this data. This is beta 1, beta 1, 2, beta 2, 1, beta 2, 2, beta 3, 1, beta 3, 2. Okay?
Okay.
I just use this formula, I can get this. For example, what is the first this one? Variance is beta 1 square plus beta 1 2 square plus sigma 1 square, right? And beta 1 is this, beta 2 beta 1 2 is this one. So square this plus square this plus sigma 1 square, right? That's what this says. Do you see this one?
Yes.
Okay. So square of 0.5 is 0.25. This is another 0.25. So sum of those two becomes 0.5. That's exactly what I'm saying. Plus sigma 1 square. Okay. It's coming. This is what this is.
Okay.
First element. Covariance is this one. Covariance formula is here. So you can just do, I'm sorry, here itself you can see beta 2 1 beta 1 1 plus beta 2 2 beta 1 2. It will become like that in the same way. This is beta 1 1 1 2 2 1 2 2. Okay. So beta 2 1 2 1 times, this is 0.5 0.35 0.15, right?
Okay.
0.15. And the next one is beta 2 2 times beta 1 2. This is also 0.15. So it becomes 0.3. Are you with me?
Okay.
Like
Yes.
that, I can fill up the whole thing. Okay, I'm just giving you a sample. If this is a structure, this is a covariance matrix out of the structure using this formula.
Okay.
Okay, this is the explained part of the total covariance here. This is the total. I can calculate covariance here, and then I can calculate the each of this one. But sigma 1 square, sigma 2 square, I don't know. So I know this in calculation. But I also know because the loadings are like this, it should be like this. So I can calculate sigma 1 square if I want from here. Because I know this is the variance. This is the variance covariance, isn't it? On the R side you saw. Okay?
Yes.
The point is if this is the structure, what is the covariance? Due to the loadings. Why I care for this? Because you remember the total variance is going to be decomposed into loadings related variances plus the specific variance or unexplainable variance.
Okay.
And this is regression. This is similar to R square. This is what we care. If this is more, it is better. This should be less. It is better.
Mm-hmm. Mm.
Okay. And here is another loading, and it will also give the same variance covariance matrix. That's where I'm going. This is another example where if you can do the same thing here, you will get these same values, this like this. So this leads to this is beta 1 1, beta 1 2, beta 2 1, beta 2 2, beta 3 1, beta 3 2. Okay, this will lead to the same value.
Okay.
Because I made the comment that in the factor structure, if you are going to write like this with those conditions and assumptions, we know how to calculate variance covariance, and this will turn out to be whether this structure or this structure, whether this loadings or this loadings, it is going to be of the same type. So it is not unique. That's my point. You can calculate in the same way I did the calculation. You can do that. You take the square of this one, plus you take the square of this. This is 0. You take the square of this. This is 1 over square root 2. Take the square root of this. It will become 0.5. Check it out, please. Both of you. Maybe I can do it here. So, are you with me? Are you looking at this? My screen here at the bottom.
Yes, sir.
Okay. So I said 1 over square root, isn't it?
Yes.
1 over square root 2. Right? And then we want that to be squared. You see 0.5. Did you see that one? I want to report this one so that you are not confused. This is about 1 over square root 2 square, right? The whole square. I should have done probably, it's better this way. It is still the same answer. Are you with me? So,
Yes,
it is same. Two different ways, two different loadings gives the same variance covariance matrix, okay? So, if you are going to optimize for maximizing the variance here, okay, you can get any unlimited number of answers, but we need to fix for one so that whatever you get as answer, Nini, I get the same thing. It's important, right? If I get something and you get something and I interpret differently, you differently, then people are going to be confused. All right. So the point is now, how do we do this? So there is a way to do that. We'll talk about it. But right now I'm talking, I'm explaining it in the geometric method. So these are the 3 points, the weights, factor weights these are 3 points. 3 points are plotted here, okay?
Okay.
BI1 is BI2, okay? And then you rotate this into 45 degrees.
Okay.
So that because the points are selected in such a way, they are on the 45 degree line, just for academic purposes, okay? They are on the points on these lines. So if you calculate now these values in the new coordinate system, it is going to have one of the axes to be 0 value, right? Here also it will be 0 values. That's what is going on here. So the new coordinate value for these 3 things turns out to be these values. That is, in fact, I know. I didn't just like that. The author didn't, just like that put it. He already was, sly guy, right? So he knows that, this is what is going to happen. So he already calculated this and then he used it. He is saying that, I can have this also as a factor. And indeed it is true. Are you with me? This is B11, this is B11, this is B12, this is B12, this is B2 minus, right? Yeah, that is B32. Okay, this point. So my point is now we have to think about this. All these things are consistently related in the discussion I am explaining. Okay, now, so what do we do about it? Let's continue to go. Okay. So every possible rotation is an equivalently error-reducing solution. And you can accept anyone, but we don't want to just leave it there. We want uniqueness of unique values. So there are so many solutions, given to make sure that it's unique. Okay, there is Verimax, there is Promax, there is Thurston, so many things. For example, I'll show you here. I went to, we can go to the help file. Go to the help file. Let's say question of FA. And you can see here. Are you able to see this one here?
Yes, sir.
Okay. So, and I just want to tell you there are so many variations, so many solutions are there. So, but you can use some very general ones. I usually use Varimax. Okay. So you don't have to use anything rotation. That is what your regular first step solution is, and then you subsequently do step 2 on the rotation so that you get the same answer. There is Varimax, Quantimax, Ventler T, Equamax, Varimin. People just do throughout that life factor analysis because of this variation. So many things are okay. So many things. This factor FA is a very interesting function. There's so many different things it can do, okay? Because of this thing. Promax, Oblimin, Simplimax, Ventler Q, Bifactor, all the very min, Geomin T, Equamax, all those things. Cluster also are possible. Okay? There are method for cluster. So, you just use Varimax, okay? Why I say Varimax, I will complete. Okay? Varimax is a rotation where it maximizes the variance, that is, these values it maximizes.
Okay.
Because that is related to how much variance explained, right? So we can keep that as one of the standard solution. Okay. Now, what I want to do is also show you. Let me go back. So first solution is, your first solution is use principal component type method. This is really also principal component. Only thing is that, so get some solution. First you get some solution, which is also principal component type, because it could be 3 scores are there, you can get 3 factors. That will be explaining the whole scores 100%. But the more the factors you include, of course, it will increase better prediction of this.
Yes.
But the smartest solution is the less the factor that explains maximum variance. Are you with me?
Yes.
Which means maximum eigenvalue related interpretations. So I'm kind of relating to principal components now. So there is a principal components hidden here also. Okay. So that's what we want to do. Our method to do the first principal component. Our method we want that to do principal component. That's what this says. Most widely used method for determining the first set of loadings is principal component method. Total communality as close as possible to the total of the observed variances. Okay, that is what we have wanted, right? So total of observed variances, we want that. That means, so the minimum number of factors are explaining maximum variance. Again, we are coming back to the same thing. Okay. Now, so here is the first you do the principal component. You got all this beta 1, beta 2, all those things. So you can calculate these things. Okay, with the communality, we know it is sample variances, and this should be very close to this one. That is the best model. Are you with me?
Yes.
Yes, sir.
Super. You
yes, sir. I got it.
Oh my goodness, this is because we got some very dense information here. Okay, that's a lot of little things going on. So
minute details.
I'm sorry.
Minute details also.
Yeah, minute details. Okay. And so we calculated these variances. Already we know this, right? We know this, so we just put it here. And then we do the principal component solution, which means unstandardized variable. Remember that.
Okay.
Okay. And so there is a principal component solution here. Okay, that will give you the unstandardized solution. That means none. There is no rotation. Okay. So we got these answers. Now the beta 1, beta B11, B12, B21, B22, B31, B32. We got all those things. Now I square them. I get the communality. That tells you that the actual variance in this variable is 9.84. I got this communality with 2 factors, very close to 9.84. Basically,
if you round it up, it's the same. If you round it up, it's the same.
It is the same, exactly. So even though there are 3 scores, just 2 factors is good enough. Almost you got 99% for finance. Marketing is also 99%, and policy also 99%. Totally, when you sum all these things, this is 99% of 99.78% of this. This is a great model, great factor analysis model. But think about it. You didn't know anything about what is the factor, what is the loading, but of course, you did the principal component type solution for the data you got, which means you are applying it for the variance covariance of the unstandardized variables. You got these explanations, and it's beautiful. One more thing is beautiful here, that is, this factor is very big, and this factor is very small, right?
Yes.
And likewise, these 2 factors are very big compared to this one. Always compared to, right? These 2 factors are very big. So this is what happens in the good models when you build. There is a separation here. So finance is 1 factor, and marketing and policies have so much correlation among them, it defines 1 factor. Okay. So this is what we want to do and explain these things. That's all to the mathematics. But here is the thing, right? We see that the solution supports the expectation. What is the expectation? That the policy and marketing are related. Okay. The loadings on F1 are relatively large, but close to 0 for Y2, Y3. The loadings on F2 are close to 0 for Y1, but relatively high for Y2 and Y3. Thus, F1 could be interpreted as quantitative. F1 can be interpreted as, something about the quantitative, skills. F2 can be related to something called verbal skills or verbal ability.
Yes.
And this kind of meaning, you as human has to ascribe. Okay? Right now with the current AI, we can't do that. Okay? But remember, in the end, AI is nothing but having lots and lots of data. If we have lots and lots of data, every variation is like humans, we can figure it out. Do you understand what I'm saying?
Yes.
Okay. So the 2 factors explain 99.78% of the sum of all observed variances. This is what this means. These two factors explains 99.78% of all observed. These are all observed variances. Explained variances this much. So 17.8811 divided by 17.92 is 99.783. Do you understand this meaning? This, you have to say such statements.
Yes.
Super. Very good. So now let us do one more thing, right? Having the total so let's do this one, okay? It's clear that the principal component method will favor all the variables with large variances at the expense of. So there are some issues, right? So if you put let's say sports, you give 500 points. Just say sports, you give 500 points, okay, or 100 points based on 100 points, and then you score ABC basically, right? And then you give it 80, 90. That will override all the other variables. So it is the problem with principal component analysis in general, right? So that's why you have to standardize principal component variables. Okay, they standardize the variables to get principal component work, even in principal component analysis. Okay, so the standardization is this method. This is your standardization method. That is, you take the so this is also called z-score. Okay, this is also called z-score. I want to get this attention to you, because I will use this many times. Z-score, z-score, z-score. Okay? That is what the standardization is all about. Are you with me? So after you do that. So these are the means, variance, standard, and all those things. And you are standardizing the variables data, and that's what this happens. The original data. Okay. Now you calculate the covariances, which is same as correlation matrix, and this is what you get. Get it?
Yes, sir.
Excellent. Up to this, we are good, right, Nini?
Yes.
Super. Very good. So now we want to do the principal solution, principal component to the standardized variables, which means basically you are doing the analysis for the correlation matrix. Okay. And now the loadings are coming out to be like this. Okay. These are the loadings. You still have almost the same explanation. Okay. All right. Same explanation. Everything is same explanation. Square this, you square this, you square this. Okay. That's what this communality. You square this communality. Square this communality. Okay. The total communality is 2.98. We have the total variance is 3. Look at this one. It's a variance 1, 1, 1, 1, right? Because it's a standardized. It's 3, and your explained variance is 2.987, which is almost 3, right? So you got your model, two-factor model explains 99.66% of total variance. Super model, isn't it? And out of this, this alone, the first factor alone has a loadings total value of 1.98. This has 1.008. So this alone is, 66% of this total. That's what this calculation is. You see this one, 198, 149, 1463 over 3 are about 66%. While this one is 1.008, 306 divided by 3. The total value is this is 3 actually, right? So this is 33%. So together is 99.659%. Isn't it similar to regression, as you said,
Yes.
Nini? Okay.
Yes.
Super. Right? Wonderful. Now, you have done all these things. This is what you have to do when you build the model. Okay. And this example actually uses SAS, but we are going to use, just, our data.
Okay.
Okay. Okay. So, and we when the factor loadings does not reveal the hypothesis, this is where, you should seek specifically factor rotation when the loadings are not supporting your hypothesis, right? You think something, when you are doing the analysis, right? You kind of engage with the data. And if your factor resolutions, right, the factor values do not support the hypothesis. See, we know that it supports our hypothesis. That factor 1 is all about, in this case, factor 2. For standardized variable, you just swap, and factor 2 is all about the really the weights are given for finance, quantitative skills, and factor 1 in this case is verbal skills, right? So when we have such expectation, your factor loading should explain that. If it doesn't explain, that's where you can use a rotation to get to your explanation. Are you with me?
Okay.
Remember that statement. When you should use your rotation. Okay? Specifically, when you can take advantage of the rotation. Let me put it that way. When you can take advantage of the rotation.
Okay.
Very good. How about Gaushali? So please make note of that statement. When you should do the rotation, you can do it, and we are going to do varimax rotation because it explains the maximum variance, right? That's our goal always, right?
Yes.
And every rotation has some advantage, but we want to focus on the hardcore interpretation, hardcore goodness of model. Okay, that's varimax rotation. So here is the varimax rotation. You can see that this is what happened. It's very close. Nothing, because it's not going to change too much, right? Because the model is already perfect model. It's the same thing is happening here, even though they did the varimax rotation. So in this case, because it is already supporting the hypothesis, it's not going to give you extra because already very close to 100% is achieved with two factors. Are you with me, everybody? So it shouldn't surprise. You should not surprise. The second question you have is, this is a very small example data set. What if you have 100 variables? Then your question is, if you have 100 original variables, let's say 100 variables are there to to understand the housing market. I am not saying the housing price, just to understand the housing market. How to explain the houses differences. Okay, there is no outcome variable there. I'm not talking about sales price prediction. Okay, just characteristics of the house. There are 100 variables. Then you can do the factor analysis, group down the loadings, and see what it could be. Everything about rooms could be one factor, one group of factors. Everything related to the neighborhoods will become another group of factors. Everything related to the economics of the house could become the third factor. You see what I'm saying, right?
Mm.
So you want to find out how many number of factors to use. If you have 100 variables, you don't want to use all the 100 variables. Then why do you care about doing the factor analysis? Factor analysis is useful if you want to reduce it into few, maybe
Few,
3,
yes.
4 factors. Okay. So when do you stop factors? Yesterday we went through this one, right? And where it is stabilizing, you stop there.
Yes. Mm-hmm.
Maximum reduction stabilizes, you stop there. Okay? So there is a scree plot, and I talked about that. You can do that scree plot, and it is same as basically related to your eigenvalues of the factor loadings, the factors, eigenvalues of the factors. Remember how much variance is explained by the eigenvalues. So that's what it is. So let's do this one here. FA. Yes, I'm going to bring that one here. So it gives you already, right? Subscores, right? And then number of factors, I'm going to say 2. All right. I will do rotate equal to Varimax. Good. It's as simple as that.
Yes, sir.
Nini?
Yes, sir.
Rotate.
So that's the answer. And there is a lot of output before. See, you see this one? This, for some reason they say MR1, MR2 is basically factors. Okay.
Okay.
And the sum of squares of this is the communality is here. This is the specific variance. This is the communality. This is specific variance, and sum of these two becomes 1 because it is already taking a standardized variables. Okay, it uses automatically standardized variable, and factor analysis using method minimum residuals. Okay, that is fine. Minimum residuals is using. And standard. Oh, it is standardized based upon correlation. That's why it is 1, 1, 1. Okay, you understand what I'm saying? These are the variances. 1 variances here, variance 1 total, and this is the basically communality plus the specific variance. And these are the factor loadings. And the MR2 refers to the second factor, MR1 second. So it is MR1 refers to. So the second factor is independent of this one because this is high, low here, and this is low, this is high. So they are perpendicular in that sense. But it's very approximate. Remember, it's always approximate, right? But it's beautifully separated out. Same thing what I have been explaining because it's the same data. So here is this the loadings are 1.98. That is the sum of squares of this plus sum of squares of this is this one. Okay. This sum of squares is this. If you square these things, sum of squares of this, you'll get this. Are you with me?
Yes, sir.
Okay. So you can just check it out. Sum of squares, you can do it for some fun calculation if you want. So let us see them. 0.1. I'm going to put everything here and then square it. Okay, 0.99, 0.99. Here it is 0.79. Here it is minus 0.08. and then 0.09. So here it is sum of squares is equal to sum of squares. There is a function, okay. You see 1.96. It says 1. Okay, sum of squares are loaded. So okay, let's see this one. 0.60. Okay, this is okay, but here it says, oh, it may be rounding error because see, this could be 9, 0.99, 7.9, and 6, and so on. So it will be 1.098. Are you with me? So they are already rounded. If you use the rounded values, you cannot get back to this one. That's my point. Are you with me? Yes? Hello? Are you there?
Oops, sorry. I'm on mute.
All right, okay. So I'll give you momentarily 5 minutes break, okay? Just hold on. I'm just saying, this is a rounded value. So because of that, before rounding, they did the calculation and it is 1.9. After you round it, if you do that, it will not be exactly this. That's my point. That's why it is 1.6. Okay. All right, this 6.3 is working out all right. All right, now how much is this? This is 1.98 is 0.66%. Okay, remember that we talked about that?
Yes.
66%. Same thing here. So this is 21%. Cumulative variance is this, and this plus this is 0.6. This plus this is 0.87. 0.66 plus 0.21 is 0.87. Proportion explained is this is how much variance explained again 76%. This is basically this divided by this. We know this is among the selected variables only we are talking about. This is a different type of cumulative variance. Okay. This is proportion variance explained 76%, the remaining is 24%, so that is 100%. So I'm saying this and this together is supposed to be explaining the whole variance. That's what the calculation here is. And cumulative proportion is this. That makes sense, right? Because 76, you add these two, then it becomes 1. So it's basically, root mean square is 0 because it's such a perfect model, right?
Yes.
And very close to 1. Very close to 99.9% is explained. That's what will happen. Agreed?
Yes.
And everything else is, the root mean square of the residuals is 0. The degrees of freedom corrected root mean square is not available. Okay. So here it says that, the degrees of freedom for the null model are 3, and the objective function was 3.89. That is coming out to be, we calculated this also. Objective function is the total variance for the standardized variables, and that is tested with chi-square model and so on. But nonetheless, this itself is good enough for you to explain and get the buy-in, what it means in the case of it. This is a very small example. If you have hundreds of variables or any number of variables, then you can see how beautifully these things can be used. Okay, we already saw in the instructions. I explained all those things to you, right? Many examples. Okay, so correlation of scores with factors is they have the MR1, the first factor, has very high correlation. Correlation regression scores with factors. Okay, is very high. And that's what we know, and this is also very high for the MR2 is also very high, right? This factor is correlated very highly. M1 is highly correlated with the scores, with the data values. That's what we are saying here. So instead of small data set like Y1, Y2, Y3, you can also have bigger data sets. Still, you can interpret in the same way. That's the conclusion I have.
Okay.
Any question? Okay, if not, take 5 minutes break. When you come back, I want to review the SVD and start the, I think review the SVD recommendation engine. I'm just wondering whether it should be recommendation or clustering. Okay, I will do I'll do clustering now first and then recommendation engineering next. Okay?
Okay.
All right.
Okay.
Come back in 5 minutes. Thank you.
Okay. Thank you, sir.
Second round.
Okay.
Okay. So now we start with, in this section, we are going to introduce cluster analysis. For some reason, observations are together or they are similar. Okay. So those two words are very, very important: similarity or togetherness. Okay. Togetherness gives you an impression of being closer. Okay. Similarity is an abstract way of saying being closer, but they have similar characteristics. Okay. In both the cases, similar things are, things that are together exhibit certain groupness, and that's what we want to find out. Are there groups together in the observations? Okay, because they resemble, the observations are resembling, having similar characteristics, similar attributes, so they can be put together as a group. Okay, and it's a very useful exercise. Again, here we don't have the explicitly defined outcome variable. So togetherness is defined by, as I said, how close it is. Together, by definition, has the implicit meaning of closeness. Do you agree with me?
Yes.
Togetherness has an implicit meaning of being closer. Okay, and in the same way, similar is also the sign of together, being closer. See, these are all blue dots, blues, items with octagons or something like that. This is again pentagon. This is maybe not octagon. 7 faces. 1, 2, 3, 4, 5, 6, 7 faces. The point is, it doesn't matter. I'm not really going by how many faces are there, but it's all blue color. This is all brown. This is all pink color. Okay. So how do we figure out what are the observations are together, okay, and which means closer, or what are the observations are similar?
Okay.
How do we mathematically calculate that and hence bring observations together as a group? Clustering is same as grouping. Okay. So the first method is, I'm going to go after k-means, right? I think it's k-means. Yeah, k-means. And let's say this is how the observations are, this is how the observations are, okay? And I artificially drew, and artificial means I drew saying that, looks like these are all together, these are all together, these are all together, and these are all together. Instead of that, it could be like this also. If there are 4, if I want to find out 4 groups, this will work. Okay, this is one method. This is not the only method, right? Possibly these things go together. This 3 is together, right? So also, and these 3 together, and these 5 together. Alternatively, if I'm looking for 3 groups, then I can say something like this. Again, this is no hard and fast rule. This is the right way. So it could be together these things, and this could be part of this thing. Okay, and what we want to do is, as I said, there is hierarchical clustering and also the k-means cluster. Let me quickly tell you what is an hierarchical cluster, but then we'll go back to k-means clustering, okay, in computations. So these points together, these and these are together closer. And then if I want to say what is the next closest to this cluster, P4 is coming. And what is closest to this cluster, which includes P4 also, then next one is P1. So by that time, it's all done. This is, so you are hierarchically agglomerating. Okay? Okay. And this one is another type of cluster, also hierarchical cluster. P3, P4 is together, and then P1, P2 is together. Okay. And then overall, all of them are in one big cluster. This is another, the same idea, but this is another way of saying there is a different type of cluster there. Everything depends on how we define the distance between the observations. Okay. So, and how we add the next observation to the previous cluster. So here, what we are saying, P2 and P3 are together. What is closest to the next observation, P1 and P4? Which one is closest to this cluster? Which means the minimum of the two distances versus this distance. The minimum of all the observation here to this distance versus this distance. Okay. So that it says obviously this is closer to this because the minimum of each of the points is still smaller than the distance between this and this. Distance between this and this, or even distance between these 2 points. So these 2 points, minimum of these two, minimum of P1 distance to P2 and P3 is more than minimum of distance between P4 to P3 and P2. Okay, so that's what this says. But if you are going to look at, this one is a different type of clustering distance calculation. So what is the first two observation closest is P3, P4, and then you take the maximum of the. You can use many different definitions. So let's say take the maximum, but before the maximum comes here, P1 and P2 are closer together. So they form together as a cluster, they form cluster, and then they together can be the overall cluster. Okay, it's a different definition here used.
Yeah.
So that's what we are going to see later on. We'll come to that. Okay, the average. So we are going to use average distance, minimum distance, maximum distance.
That also reduces the clusters.
Oh, you mean the number of? Okay, so now the question is what is meant by number of clusters, right? That's what you just now attended to, number of clusters, right? So how do we determine number of clusters in these cases, right? So then what we have, what is that called? The distance defines the distance that separates the cluster points is what defines the clusters, right? So the distance is the vertical axis. If you put the distance here, it is 4 here, and if you put the distance almost the same here, almost the same here. It may not be almost same, but I'm just telling you it's also having 4. It depends on where you cut the distance. Okay. But you are right. This what kind of, when you have a cluster of points, how do you define? Is that the minimum or the maximum or the average distance you want to use? That defines how the structure will develop. We'll come to that here.
Okay.
So let's first finish with K-means. Okay, K-means is a very simple, very important, highly used clustering method. So what it says is you randomly choose K objects as the initial cluster. Okay, so here let me go to this one. These are the 8 points we have in the analysis. Okay, this is x-axis, the y-axis 1, 2, 2, 5, 2, 10, 4, 9, 5, 8, 6, 4, 7, 5, 8, 4. Okay, that's what this 8, 4. I might have said 8, 4. Yeah, 2, 10. All those points are already written like this here. Okay.
Okay.
Now, we have to, in K-mean clustering, that's why K comes first. How many mean you want to use, how many means cluster you want, how many clusters you want. K, you need to know before you start. Okay, that's one of the important conditions. So you say we want 3 clusters, we want to find out 3 clusters. Okay, then you randomly select 3 points. Then let's say C1 is this one, this is C2, this is C3. Okay. Now, start, C1 is 210, right? C2 is 58, C3 is 12, right? You randomly selected. Let's say you are randomly selected, okay? You are randomly selected. And those are the 210, 58, and 13. And 3 clusters, right? You find out the distance from that each of these means to each of these points. So for example, 210 How far is this, 210 from 210? Of course, zero distance. It's the same point, so it's zero distance. So now I have to know how to calculate distance. There are many distances you can calculate. This is one of the distances. This is the what is called the absolute. This is also called the Manhattan distance. Okay. So here is the example. Because in Manhattan the streets are perpendicular, kind of, right? So if you want to go from here to here, you have to go on this axis, however many number of steps you have to go on this axis, and then go on this axis. So when you go on this axis, this has zero values, right? Nothing changes. When you go on this axis, this has zero value, right? So you can just take on this axis absolute difference from here to here, and then you add the absolute difference from here to here. That will be your total distance. So this is called Manhattan distance, okay? And for example, from 210 to 210, the mean point is 210. That's what we are fixing. The randomly selected point is fixed to be your starting point, and for that starting point, for that cluster, the mean is 2, 10. If you have 2 points in the cluster, then you take an average later on. But right now, only 1 point. And what is the distance between 210 to 210? It is, you just apply this formula. You don't have to give any logic. If you apply it, it's 0. Do you agree with me? X2 minus x1 plus y2 minus y1, which is equal to 0, 0. In the same way, what is the distance from the center? I'm going back here, applying, and I'm going to apply that. What is the distance between 210 and 25? So 2 minus 2 is 0, 10 minus 5 is 5, absolute value 5. Okay? Super. And then what is the distance between 210 and 84? 6 plus 6, 12. Agreed?
Yes.
And what is the distance between 210 and 5, 8? It is 3 plus 2, 5. Okay? What is the distance between 210 and 75? It is 5 plus
5 plus 5.
5 plus, 5 plus, I'm sorry, 2 plus 5, 7. Okay?
2? I thought, isn't that
7. This 2 to 5, I'm sorry, 2 to 5
2
is
to 5 is 2 to 7 is 5.
5 plus, this is wrong.
And then
It should be 10, isn't it?
yeah, this is
Right?
yes.
Okay, thank you. I was working. Maybe there is shifted the numbers again. We'll see. This is how much the distance between 2, 10 to 6, 4. This is 4 plus 6, 10. This is also correct.
10, yes.
And 2, 1, it is 1 plus 8.
1 plus 8, 9.
And then 4, 9 is 2 plus 1, 3.
3.
Okay. I'm sorry.
1, 3.
Is okay?
2, 1, 3.
2, 8. Oh, 2, 1. Yes, isn't it? 3. Do you agree with this?
Yes, sir.
Do you agree with this?
Yes, sir.
Okay. So let's finish all these things like that. The distance between 5, 8 to 2, 10. Finish this one. If you finish it, you do all these things. This is what the answer you will have it. Okay?
Okay.
If you want to finish that yourself, why don't you do that? Just a little bit of exercise. Will it hurt or work out better? Warm up.
Yeah, just a little, but it is I get it.
Okay, you get it. Okay. How about you, Gershali? You good?
Yes.
So we are going to our question is this. Okay, the question is, which of these 8 points are closer? Which of these 8 points are closer to which of the means? Right? That's the question we answer. So this is closer, of course, to. So there is no. It's a trivial information. Okay. But other than its own mean, other than its own points, that's, if you want to say, isn't it? So, in other words, this point is closer to this one, so leave it. It will belong to 1. But 2, 5 is closer to which one here?
4.
4, which means it should be assigned to cluster 3. That's what we are doing here.
Why cluster 3, sir?
Because it has the lowest distance from its mean.
Oh, okay.
So the closer the one, you should say it belongs to.
Okay.
The togetherness.
Okay.
So next one is 8.4, which is the shortest distance among these 3 means.
Okay, so 7.
Which is 2. Assign it to cluster 2. This is the cluster assignment. Okay.
Okay, I see.
So I can put it as assigned cluster. Okay. Now next is 5.8. It's closer to its own, so it is not going to change. It is 2. 7.5 is closest to 2 because it has at least.
Wait, can you go back to A4?
8.4, okay.
No, A4.
A4, okay. 5.8.
Yes, 5.8. So shouldn't that be cluster 1?
Why? It is.
Oh, you're assigning itself.
One point. It's a trivial calculation. It's 1 point. This 5.8 is same as its mean of its cluster. It's one cluster.
Right.
You are not going to change that. It is 2. Okay.
Okay, so you're assigning itself. Okay.
So 7.5 is lowest together. It is closest is with the 2. So we put it assign is 2.
Okay.
6.4 is closest is to 2 because it is the minimum is at 5, so assigned to 2. 1.2 is its own mean, right? So it doesn't matter. It's a trivial point. Keep it as 3. 4.9 is together with 2 because it's the closest distance. 2.
Yes.
So these are your assigned clusters now. Okay.
Okay.
Now once this is what it is, if you once you assign it, okay, this is what it is assigned. This is 1. All these points are assigned to 2. These 2 points are assigned to 3. See, there are 2 3s and 1 1, and rest of them are all 2. So that's what this one is. But now you calculate the mean of this cluster, and then mean of this cluster. There is only 1 point, no problem. This mean of this cluster. Now for each of the points, you calculate the distance to different means, and based on that reallocate again. So if I do that, first of all I need to know the mean, right? The mean of the cluster 2 is all the x values mean, y values mean. It is 6.6. For cluster 3, all the x values and the mean, all the y values are mean. So it is 1.5, 1.5, this 6.6. This one doesn't change, it's 2.10 again. Now I complete this one again. Are you with me?
Yes, sir.
So
Yes,
that
sir.
is what these centers are. New centers are this. New centers are this. I calculate the distance. So this is same as this point, so it is always be 0. So now I have to do the calculation. So this is an Excel file because of that. Okay, so I did that using calculation of Excel. See this one? Absolute. So absolute distance between 2.10 to 6.6. That is 4 plus 4, 8. That's why it is 8. But this one is very tricky because 1.5. Although it's a fraction. But you can do the Excel. So I did the Excel here. So it is 7. I filled up all these things, okay, and I start assigning the cluster again. Okay, let's do that. So this is not going to change. It is 1, cluster 1, but 2.5 is closest to which?
3.
It is now 3, right? Maybe last time also it was 3, okay?
Yeah.
And then 8.4 is closest to what?
2.
2. So 2. 5.8 is closest to 2, so it is 2. 7.5 is closest to 2.
2 again.
So again, 6.4 is closest to 2. Again, 1.2 is closest to 3. 4.9 is closest to 1. Okay.
1.
Now there is one change. The rest of them are all the same. The one now we have 2 ones now. That's the benefit with this iteration.
Okay.
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 I repeat this again with, so what happened? I have 2 points here. Now 1. So its mean is changed now, right?
Yes.
And 3 its mean is not changed. Okay. But the one's mean is changed, and this one, one's mean is changed, and 2's mean is also changed because one's mean is changed. 3 is not changed. Okay. But nonetheless, in the third iteration, the new centers are these values and the average of the points within the cluster. Okay. 1 is changed, 2 is changed, 3 is same. That's what it means. Okay. Now I do the same calculation, distance, and see closest. So 2, 10 is closest to 1 again. So 1, right? So that's, this time I'm getting one more 1. You see this one more 2 is changed because it's 3.5 is the closest to 5.8. So 5.8 belongs to the cluster 1. Cluster 1. Are you with me?
Yes.
Okay. So after this, it will not change. Once it is not changing, you stop.
Okay.
That is your stop rule. Stop rule is the clusters, because if the clusters don't change, the means don't change, the distance values are not going to change. Right? If the clusters don't change, that means the mean values don't change. That means all your distances don't change. So it is converged. The solution converged.
Okay.
Okay. Now that is one way, right? Now the other method is I want to calculate the distance. Okay. I want to calculate the distance. So distance calculations are easily done. So, this is iteration to all those things. We have done it. Okay. We have finished. I don't know why it is here. It doesn't have to be there. So let's finish the k-means. What are the? Is it a greatest of greatest cluster, or are there problems? We'll have to look into that. Okay. So let's look into the caveats of cluster, k-means.
Okay.
So if the the sizes are too big like this, varying sizes, then k-means can be problematic. Okay. Because if you say 3, these points will be closer. These points will be, I don't know, these points will be closer, something like this. These points will be closer, okay? And these points will be a separate one, isn't it? So to avoid this, the general strategy for all the things that I'm going to talk to you below, the general strategy is just use lots of different smaller clusters and then combine them.
Okay.
Okay. So if you have just 3, this is what will happen. It is blue, but it will ask for all these things. It will ask for all these things. The remaining will go into different. So if you do lots of different small clusters, this is one cluster, this is one cluster, this one cluster. So it's asked for let's say 10 clusters. Then it becomes the cluster of clusters will be we'll get back to these kind of clusters. Are you with me?
Yes.
So here is another example, right? Look at this one. If I have data like this, then different densities, right? Then if I ask for 3, this is what will happen. This will become together because their distance to these things are too far, right? But each of them are much closer, say they will become together.
Together, okay.
Yeah, so this will become another cluster, this will become these together, two things will become another cluster, which is not good. Consider this one, okay? Again, the same thing, right? Even though it is This is the real cluster, right? But then it will separate out to be all tops will be one cluster, bottom will be another cluster. Agreed?
Mm-hmm.
Okay. It's a problem, right?
Yes.
So the strategy for all these things, as I said before, the strategy for all this thing is, use lots of, small clusters and then combine them. Then it will become like this. Because this is closer to 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 this. Eventually, these things will become one. This will become one. Maybe a little bit of it depends, but it depends on the distance here, right? So if
Yes.
each of these distance together is as you aggregate these smaller clusters, it is never bigger than this distance, and then it's okay. Otherwise, this will belong here. Are you with me? It depends on how they are distributed. That's what I'm saying. Okay.
Okay.
Again, the same thing. I said multiple small clusters. If you do that, it separates out here, and then they all together here, so it will become fine. Same thing. Multiple clusters here, clusters here. This is closer than this to this, or this to this, or this to this one. So they go together. Its average is this one. This is as long as this average is this distance between these two. The new average here, right? The average will be here. The distance between this average and that average is smaller than the distance between this to this or this to this, then they will go together, continue to go together. Are you with me? So you need
Yes.
to have lots of smaller clusters, then it will work.
Okay.
Clusters, it will work. Okay. So that defines the K-means cluster. Now I want to talk to you about hierarchical cluster. Okay. So let's take these points here, whatever it is 1, 3, 2, 5, 4, 6. 1, 2, 3, 4, 5, 6, 6 points, right? Dimensional plane, it is sitting there like this. So this is the closest, I don't know, visually it looks okay, closest. This is also closer, but
Yes.
closest together. So this is one cluster. This is one cluster. Now the problem becomes complicated. Where should 4 go here? Should it go here or here? It's very clear it should go here, isn't it? Because the distance between 4 and 5 and distance between 4 and 2, the minimum is with the 4 and 5. Okay? And then only comes here. So it should join with 4, 2 and 5 together should join with 4 first. That's what is happening here. It should join with 4 first. And then it joins with this. Okay? And then eventually, it joins with the 6. Are you with me? Very important, how these things are joined. And I'm going to talk to you about the mathematics of it, coming to it. Hold on a second. So when we have, groups already together, you can calculate the distance between the groups in one of these four ways. Either you can use minimum most of the distances. So that means these 2 points determines the whole clusters coming together. Or the maximum distance, that means this and this point to these 2 points determines, okay? Whether these points should come together with this or with some other group of points. For that, either you can use the minimum, maximum, group average, that means here to here, okay? Here to here, group average. Or Watt's method uses squared error, something called squared error. That's another method, okay? Let's use our R uses these 3 things, commonly: minimum, maximum, group average. Okay, are you with me so far?
Yes.
So you need to have the proximity matrix or how close each of them, which means basically you have to create a distance matrix. Okay, are you with me?
Yes.
All right. So now the minimum is also called single link. Okay, because it is just the only one. This and this is what determines. Single link is determining whether the cluster should be joined or not. The maximum is also called It's also called a single link, multiple link. Wait. Single, still working on max link. Okay, max or complete link. Okay, because it links the complete. If I take the maximum of this and this, it links completely, because when you consider this as the standard to combine together, all the other links are sub links, suboptimal sub. It is less than this one, so it is what is called the completely linked. By the time you come here, all the other points are linked also. So it's called
Okay.
okay. And then the other one is average link, group average link. So either one you can use. Okay, so let's talk about it. So here is the distance matrix. Distance matrix is for each of the points how much distance is there. It could be as simple as Euclidean distance. Okay.
Okay.
No. So we will use Euclidean distance. Earlier we used Manhattan distance, right?
Yes.
And this time we'll use Euclidean distance.
Okay.
Okay, so stay put, because I'm going to talk to you with some with some data. Our R will do quickly what we want. Okay, so let's talk about this one. This is your distance for 6 points. Okay, so if you look at it, the minimum most is happening at P3, P6, so 0.11. That's what. So you first link those 2 points. That's at by 0.11, only 3 and 6 are connected. Okay, up to 0.11, only 3 and 6 are connected. And then you keep increasing the distance, right? Next is 0.15, right? Agreed? 0.15, is that the next one? Let me see, 0.14 is there. 0.14 is there, okay? That's the lowest. Agreed, everybody? 0.14
Okay.
is next, okay?
Yes.
So when it comes 0.14, P5 and P2 are, 2 and 5 are connected. So that is separately getting connected, 0.14. Next comes 0.15. By the time it comes 0.15 distance, by the time 0.15 distance is coming, then, this one, 3 is connected to 2, this one, right? And then 3 is connected to 2. What else? Is there any other 0.15? 3 is connected to 4 also, isn't it? 3 is connected to 2 and 3 is connected to 4.
Yes.
So by the time you reach 0.15, 3 is connected to 2. That means these two are connected. Okay. When it reaches 0.15, these two are connected. 3 is connected to 2. That means this group is connected to this group. That's what I'm saying. Right?
Yeah.
And by the time it is 0.15, also 5 is connected to 2. So 5 is connected to 2. We already finished, right? 5 is connected to already.
Yeah. And then 3 and 4.
3 and 4 is connected. That's what it is. Okay. 3 and 4 is connected. That is it. This one. So let me put this, and then you will probably, it's better to put some notation there. Okay. Okay. So these are all it's happening. So you need to keep track of it. That's why otherwise you lose track of that. So many things going on, right? 0.15, where is it? Let's see here. Right? All these things are connected. That's what it says here. 3 and 6 already connected. 3 is connected to 2, and then 3 is connected to 4. By way of this 0.15, by way of 0.15, it is connected to 4. Okay. But even before that, this is also, I want to bring it up to you. even before that is, let me see, I'm going to give a different color here. Okay. Where is 1, 4? There is also 1, 4. This is the same as symmetric, but anyway, I'll just put it there also. Right. See. Okay. It is by symmetry, but it's already connected. 2 and 5 are already connected by 1, 4, but by 0.15, all these things are connected. That's what this one is. Okay. Is everybody good?
Yes.
And by 2, 4 is connected with 4 is connected with 2. I don't have to worry about that. Okay, it's already connected. But the 1 gets connected to the 1, P1 gets connected at 2.2223, right? By way of that, so 1 is connected to 3 at 0.22. Agreed? That's the next minimum. Agreed?
Yes.
So when it reaches 2.22, everything is connected because 1 is connected to 3, so it's connected to everything else. But if you think about all this thing, I'm using minimum only. I'm not talking about 0.24 here, for example. I don't even wait to reach 0.24 to get connected to all these things. The moment it reached 0.22, I'm connected to 3, so I'm connected to everything else. So I'm using what is called the minimum distance. Okay. So mathematically, what I'm saying is, you take first 3.6, and then I calculate what is the distance with respect to 2, which is minimum of distance 3, 2, distance 6, 2, which is 0.15. Okay. Now, next, I'm also calculating with respect to 5, 4, and 1. That's what this one, all these things. When I look at these things, so I get, if I don't have this one, I'm saying, right? When I don't have it, I'm using this minimum or single linkage approach. This is called single linkage. So minimum of the distance between the cluster 3, 6 to 2, 5, 4, 1. And out of this is 2 is 0.15, 4 is 1.15. 2 is 0.15. Okay. So before at 0.15, 2 is getting connected to 3.6. That's what I'm saying. Okay. Are you with me?
I think so.
So also the 4 is connected to the same group. Okay, by the time it reaches 0.15, because of these calculations. Now, how do I think about the next one? Next one is, I take the out of these points, we calculated this. I'm just calculating. I'm calculating one more? No. Okay. So here 3 and 5 is distance. 3 and 5 is 0.15, and distance 6 and 4 is 0.22. Okay, so the minimum of this is 0.15. See, I kind of already talked about it. I think the way I already explained it is much easier than, you could see that, right? 3 and 6 are together. The next point is, what is that point I have to connect? So I keep increasing slowly the distance, and that means I'm looking for the next minimum here. 2, and by that time I keep going. By the time when I come 0.14, these are getting together because they are neighbor. By 0.14, they are neighbor together. So they get connected, and then I keep increasing the distance. Next is 0.15. When I come to 0.15, the minimum is happening between 3 and 2. 3 and 2 is 0.15. So 3 and 2 is getting connected means this is getting, this the whole cluster is getting connected because 2 and 5 is already connected. So as I increase this distance, this the whole cluster 2 and 5 is getting connected to this one. That's what, but that's what is connection 0.15. Yeah, are you with me?
Yes.
Okay. So I complete this graph in that manner, and that method is called a single link. Okay. It is the same thing here. Whatever I'm explaining here, is in one picture. I already explained everything. Okay. These multiple colors are done in multiple sheets in this way, like this. Okay. So this is how it is done. Now, the other method is so let's talk about the strength of minimum linkage, right? Minimum or single link. Okay, minimum or single link. If the original points are like this, it will clearly separate out two clusters. Okay, can handle non-elliptical shapes also. Okay, can handle non-elliptical shapes. So it works out very well. The small versus large groups, still works out, separated out very clearly. You don't need all those multiple clusters and then combine them together that happen in k-means. Okay. Of course, it is all clusters are affected by sensitivity. They are sensitive to noise and outliers. Okay, to an extent, they are sensitive to noise and outliers. So now let me talk to you about the complete linkage. Okay.
Okay.
Now, so when I have 2 points, there is no minimum or maximum. Just we have only 2 points, so we start with the first coming together is 3 and 6. Done. Okay.
Yes.
Now I take the distance. Okay. Now I have to say minimum of the maximum. Always it is minimum, but minimum of minimum versus minimum of maximum. Now probably it is clear. So let me copy this and post it there also. So it is always minimum, but whether they want to take minimum of minimum or minimum of maximums, okay, or minimum of the averages. That's what we are talking about. Minimum of the minimum distances. With respect to the whole group. Wording is minimum of the minimum distance with respect to the whole group. Maybe it's better with respect to the whole group. Okay. Does it matter? Does it mean to you, Nini? By the time we reach the minimum of the minimum distances, so the minimum distances with respect to the whole group. So if you have multiple points, then you know what I'm saying. Okay.
Okay.
So here, what we are saying is, think about this very carefully. I'm saying. So here I am saying minimum of the maximum distance. So here 3 and 6 is first joined, and now I'm going to see whether each of the calculations I have to do, okay, with respect to one, with respect to, because by the time so this is done. The next minimum distance is this, right?
Yes.
Now that becomes a group. Before I see when this is going to be joined with this, right? This becomes a group. This becomes a group. The question is, when does 4 will 4 join with this first or with this?
Okay.
That's the question. So we're saying the maximum of the distances of the one, this one, with respect to this one is 20.23 with respect to 2.5. So you're going to take the maximum of the distance, that is 0.39. And then next one is 3.6 to 4. That is 0.22. And then 2.5 with respect to 4, that is 0.29. 2.5 with respect to 1, that is 0.34. So among all these things, the minimum is what? 0.22, right? 0.22.
Okay.
So the next one should be 4 joined with 3.6. That's what we are saying. So
Okay.
that's why the 4 came here. Okay. And it is
So it's a minimum of the maximum.
minimum of the maximum. Yes.
Okay.
Okay. So that is what complete linkage is. So, you can fill up this graph. Okay.
Okay.
Now, so again, I am doing, after it is joined, 4 is joined, I am redoing all this calculation. Okay, 2, 5 with respect to 1, and then 2, 5 with respect to all these points. The maximum distance is 0.39, it's 0.34. So 1 joins with this first before it joins with this. Are you with me?
Okay. Yes.
That's what this one is. So one more calculation, it is done. Everything is joined together. And this is less susceptible to noise and outplay. Okay.
Okay.
So you can see all blues are together here. Okay. But, not only all blues, there are some additional points are here. This is more closer to, these spots are more closer here. This is more closer to this. These are more closer to this. These are more closer. These are more closer to this. Okay.
Okay.
Limitations of maximum is that it tends to break large clusters. So if you have like these 2 different clusters, these things will become massive one cluster because these are all closer to this one.
Okay.
So bias towards globular clusters. So globular means bigger ones will be biased. So points will be gravitating towards the bigger clusters. Let's take average instead of the neither minimum nor minimum of minimum or minimum of the maximum. Let's take minimum of the average.
Okay.
That's what this one is. So first again it joins together here, 0.11 because of the 0.11. But now you take the distance to be the average distance, not the maximum distance.
Okay.
Okay. So the average distance is you can calculate that that average distance between this and this. There is the average distance is the distance between this and this, okay, which turns out to be 0.225. You do that for every one of the points, whether which one should be joined first, right? Whether 1, 4, 2, 5. And you see 4 is the lowest, again, minimum of the average distance. Okay.
Okay.
So like that, so that means 4 joins first. So it is happening because 0.185. At that point only it is joining with 4. Now we complete that. Next one is, before I go to the 0.14, this is also pairwise, distance is already 0.14 only. So at 0.14, before 0.18, 0.14, this joins together. Okay. So they become together, 4 becomes joins with this one, and then everything, 1 joins with everything. That is what is happening here. Do you think you should calculate this one at least, or one of this? I think hand calculation is important, I feel.
I think so.
You want to check it out on your own, Nini and Gaushali?
Can we do at least one? Can we do at least one of it?
For the group average?
Yes.
So, okay. So let's calculate this one. This distance, 3, so we have to check it out at each of the points, right? Is it what is the average distance? So the distance between 3, 4 is distance between 3, 4 is this, right?
0.15.
That's what this one is, right? And then distance between 6, 4 is 0.22. That's what this is. Are you? Let me.
Okay.
This one and this one. Okay. Now there are 2 distances there. So what is the average here? 6 point. They add this and divide by this. Okay. So 0.185. So the average distance is 0.185, right? And likewise,
why is the denominator 2 times 1?
It is good enough if you put 2. I'm not sure why. I think I took it from a book. I don't think you need that one. Okay. And it's funny, he is doing it consistently. So that does bother me. Okay. He's doing it consistently. All right. So next is point, the average distance is 0.185, right? After, so you have, the 3 and 6 together, and we want to know which one should be added to that 3 and 6 next. Before, before other points, right? So 3 and 6 is, that distance is 0.18. But at 0.18, you will join 4 with 3 and 6. That is the lowest. It happened here because of the previous page, right? That happened. But what I'm saying is, there is also something happening between 2 and 5 before even 0.18 is joined. That's why this has to come together first. And that is happening at 0.15.
Yes.
Good. So that is done, and this is also done now. Okay. So now that this is what it is, right? All the three are done. From here, you want to find out which, the 3162 distance 1, 3162 2, 3,6 1, 3,6 2, 3,6 4, 3,6 5. Okay. All right. So we are trying to get the average distance, in this setup. So actually it is done, so we should go to the next one. Actually, this is done. It is repeated twice, because I'm just explaining the same thing here. Okay. So now, what happens, right? So we have 364. It's combined together already. It's a group here. This what is 364. It's one group. 5 and 2 is another group. Where should one join? That is the question we need to answer, right? In the next.
Okay. Yes.
So that is what you hear. So you take the 364 to 1, 364 to 2, 5. So this is and 364 2 5 to 1. So the whole thing to 1, this to 1, or actually this to 1 also we should know, right? But what happens is, let me explain here. 364 to 1 is 0.273. So 3 and 6 and 1, so 0.273, that's what it's going here. And you will see, rest of the calculations, let's see. So distance between 3, 6, 4 with the respect to 2 and 5, okay, that distance is 0.26. This is 364 to 1 is 0.27. So this has to be connected to this. That's what, these two need to be connected to this one. That's what this is happening.
Okay.
Before it connects to 1, because it's 0.27.
Yes.
That's it. That's the end of the story. It's done. But you don't have to worry about these things. Your R will get you the answer. Okay, so let me show you the R calculation. Okay. Okay, so here is the R calculation, right? The same data. I don't know whether you were able to recall. Okay, so this is the points. You calculate distance among these 8 points. D11 is the distance metric, that is this one. Okay, are you with me?
Yes, sir.
Okay. And you can plot the distance if you want, but that's not the most important thing. So we want to do hierarchical cluster, the dotted line, the hierarchical cluster using the distance metric D11. That's all we are saying. So this is the plot, and then I kind of hand calculated the plot of this one and then hand calculated. Don't worry about it. So let us do this single linkage. When I do the single linkage, we are talking about the minimum. You remember that minimum? And this is the really the actual cluster, but how you draw the cluster. Look at this one. This is giving output looks like different from here, right? Because it's all hanging and so on. Always use this one. Okay, it's called the command here itself is something like hang is nothing or something like that. Or hold on a second. Okay. So this hang, yeah. So if a negative value will cause the labels to hang down. Okay. The fraction of the plot by which labels should hang below the rest of the plot. So below the rest of the plot. So this is what it is. And a negative value will cause the labels to hang down from 0. Okay. So if you want, we can do that right now and check it out. So here we have, let me go back to this one. Okay. D is equal to D1. Let me put it at middle frame C 2, 2, 8, 5, 7, 6, 1, 4, and then another column is 10, 5, 4, 8, 5, 4, 2, 9. So let's just do the we want H cluster. H cluster, we have to do H cluster. We need a D1, okay? Single H cluster. Okay. D11 equal to distance D1, okay? Now we will do plot H cluster D11. Okay, so if you do hang equal to 0, unused hang, wait, what does it say? What did it say? Hang, the fraction of the plot by an object of the by label should hang below the rest of the plot. Okay, a fraction of the plot. A negative value will cause the labels to hang down from 0. So let's say -1. Okay. Oh, minus negative hang down from 0. I didn't do that automatically. It was showing this answer, isn't it? If you look at it, plots, it was showing this answer. 4, 8. This one 5, 3, 6, 5. 4, 8, 5, 3, 6, 5. Let me do this. Reach this side. Okay. So when I do the hang, when I do just the H class D11, I get this answer, which is same as this one, except that it is not following fully up to this one. Okay.
Yeah.
I hope it doesn't bother, but then there is a way to get that also up to this one. Okay.
Okay.
This one is really it is also hanging here up to that, right? This is what I added just to show, right?
Yes.
Without that, it was 2, and so the number will be like that. Okay? So this is single cluster. There is a way to get all these things down up to the point. We can do that. That's not a problem. But you can see that it is the same thing here, like this. What is this one? Is here. It's a complete. Okay, when we don't do anything, it comes out to be complete. Okay.
Okay.
Then, or you can say like this. Then you can see this is single cluster. Okay. And also you have the average. This is the average. Okay. So this is complete. This is single, complete, and I don't think I have average here. The average I did bring together here, okay, in one shot. So complete engulfing or enclosure function, average distance. So by using the, you can use whatever you think is the relevant thing. Complete cluster or the average cluster seems to be better because it's not working with the edge points, right? You remember one of the advantages of complete cluster is that it is less sensitive to the outliers, right? Remember that? So use complete cluster in general, but these are 3 different ways you can create the clusters. So what I want to do is in the cluster next class, next Friday, US time, evening 7:30 p.m., I will complete with what is called DB scan and epsilon method. Okay, that is the usually not taught, and but it is a very beautiful, very nice, very simple method that is less sensitive to outliers, and you can also find out all kinds of shapes. Very interesting. In fact, that I would say that you can even use it for image clustering.
Okay.
So with that, we close our session today. Any question?
I didn't remember us talking about the outliers, sir. So I'm not sure if I captured that.
Which one?
In this clustering, I didn't remember. I didn't recall us talking about the outliers.
You mean in the DB scan, vis-a-vis DB scan, or in general?
In general.
You never heard, sensitivity to errors and noise and outliers? Is that to your point? You never heard of cluster analysis being discussed in relation to outliers?
Yes.
Yeah, you will not. For example, we don't talk about these things, right? We just cluster it.
Yeah.
But
yes.
I'm saying DB scan is a method which actually, takes care of those issues.
Okay.
So it will be, it will become less sensitive, absolutely, incredibly less sensitive compared to all these methods.
Okay.
The K-mean is very sensitive to outliers, noisy data. If you don't want to say outliers, that's okay, noisy data.
Okay.
So we'll see that in the next class.
Okay.
Thank you very much. Yeah, that's a good question.
Yeah.
Vaishali?
Thank you, sir. No questions, sir.
All right. I hope you had some good session today. Talking.
Yes, sir. Yes, sir. I have some noise issues. That's why I'm able to.
No problem. Thank you very much. Have a good night to you.
Thank you. Thank you, sir.
Great day.
Thank you, sir.
Great day.
Yeah. Bye. Bye.
Bye-bye.